Okay, let us see today how to solve a differential equation with the help of Scilab. There is an inbuilt function in Scilab which is known as ODE, that is ordinary differential equation, which solves your differential equation. Let us first try to understand the problem statement and then try to solve it. Let's say there is a reaction going on, A giving B. It's an elementary reaction, so it's a first order reaction with rate constant K1. The value of K1 is given as 0.2 minute inverse. If I write that as an ordinary differential equation, we can write that concentration of A changes with time as minus K1 into Ca, and concentration of B would increase as a K1 into C, that is positive. Now if I write that as an equation, it is C dot equals to minus K into Ca. This I'll need to solve. Now I can solve it with some analytical solution or with the help of some numerical method. Naturally Scilab will do it with the help of a numerical method. What do we require is the value of K1, initial concentration of A, and the time frame for which we would like to integrate the equation. So let us go to Scilab, and wherein I have already written the code. You can see that I have written function C dot. This is the output variable. First order is my name of the file. T is the time, which is independent variable in ordinary differential equation. It can be T, it can be any other form, any independent variable which varies from initial to final, and your dependent variable, which is concentration in our case. So this is written as C dot equals to minus K into Ca and function. So what will happen is Scilab will integrate based on this equation. I'll require to give K. It is given K is 0.2 minute inverse. You can change that. We'll see how that affects the final answers. We say that initial time 0 and final time is 20 minute. However, in Scilab you have to give that as a range. You can't just directly give final time as 20. You have to give the range starting from 0 to 0.1. Like this 0.1 makes it to increment of points. So 0, 0.1, 0.2, 0.3, 0.4, like that it will go up to 20. Then the calling syntax Ca, which is nothing but your concentration, is ODE. Ca0 is your initial concentration of A. I need to give that. This is as a comment I have given, so I have to write Ca0, Ca0, and that will be equal to 1 mole per liter. And then I have to give T0, that is initial time, Tf, that is the range of the time, and then the function wherein I have written all these equations, so that is first order. Once I'll press this, I'll run this, I'll get the values of Cf for every time starting from 0 to 20 based on RK4 method, and then I can plot that. So let us see this in the in Scilab. Let's execute this, and you can see that the concentration of A is falling down from 1 to almost 0 within this 20 minutes. Now if we want to check this, if we want to change this, say we make it 0.5, that means our reaction will be faster, and we execute that, and we can see that this is your second curve, and it is much faster, isn't it? It almost reduces to 0 at 11. If I want to make it slow, I make it 0.05. Save it, run it, and you can see that it is much slower compared to this. In fact, if you want, you can give different colors to this as well, that we'll see separately. So this is how you can do it. Now say we have this is only single ordinary differential equation. Say we have more than one equation, that is more than one variable. We have multiple reactions wherein A gives B gives C. This is a very classical example of a reaction in series, and we want to find out the time at which concentration of B is maximum. Now if I write corresponding mathematical equations, it will be dCA by dt is K1C minus K1Ca, dCB by dt is K1Ca, which is B produced minus B reacted to form C, and dCC by dt is K2Cb. Initial values are concentration of A 1 mole per liter, BC 0, K1.5 and K2.2. These are also elementary reactions. And this, if I want to convert to Scilab, I can convert this C dot into one matrix. First element being minus K1 CA1, second being K1 into CA1 minus K2 into CA2, and third being K2 CA2. So this I have to give as a matrix. Let us see how do we do that in Scilab. So I've already written that code. I have put that as a comment. I'll put, I'll remove this, and I'll write here minus K into CA, so that it will help me when I have to do this again. And I'll get rid of this. So my K1 is 0.5 and K2 is 0.2. So this is what I already given. T0 is 0, same initial to final time. CA0, now since there are three terminology, my CA0 would be 1 0 0. That means 1 is for A, 1 is for A, B is C, 0 0. I'll again use the same calling syntax. Now what I'll do is, now I'll plot all the three differently. So what does it mean? It means that this is my time profile, and this is the profile of concentration of A, concentration of B, concentration of 3. This indicates first row each column. So whatever number of points are there, CA will be populated as rows and columns. So my all the rows, all the columns, first row, all the columns corresponds to CA. Second row, all the columns corresponds to CB. Third row, all the column corresponds to CC. So this syntax is first row each column. Suppose if I want to plot all the rows for a column, I have to put each row here, column here, and one here. So this is how I do it. I'll save this and I'll execute this. And you can see that this is a classical figure which we already know. This is the time at which your B gets maximum. If I want to check the effect of K here, I can make first reaction fast, second reaction further slow, and I clear the figure so that it doesn't superimpose on that, and I execute it, and you can see that this is much more than the previous one. So that is how you can play with it. You can even say that my initial concentration of B is 0.5 or 0.2, let's say, and there is no C initially, and let's say I make this second reaction faster, wherein the final concentration will be lesser. Let's see this. So this is how it starts with 0.2. This is how you can play with this, and you can simulate any ordinary differential equation. Ordinary differential equations are frequently encountered in chemical engineering, because any unsteady state model will eventually end up into ordinary differential equation. So solving ordinary differential equation is something which we should we should be very efficient at, and neither your Excel nor your HYSYS will be able to give you this dynamic. Polymath has its inbuilt ODE solver, so you can very easily put into it. So yeah, Polymath is there, but if you want to really plug in, want to see how it changes as a kind of programming language, you can make this variables as getting input from the user, and you can solve this. So I think if you really want to see the impact of various parameters, Scilab, solving an ordinary differential equation with the help of Scilab will be much better compared to any other tool. This is how you can solve ordinary differential equation in Scilab. I hope it will help you to solve other kind of ordinary differential equations as well. Thank you.